Okay, let's continue with Valgrind. Um, let's see here. Okay, cool. I'm selling some computer parts, so just I might have to cut this short. Just basically an old computer case that's um hopefully just works out well for someone. Okay. Software forensics using Valgrind. It can take an achingly long time to track down bugs in large complex programs like spies. So C hackers have written tools that can help you on your way. One tool used on the Linux operating system is called Valgrind. Valgrind can monitor the pieces of data that are allocated space on the heap. So things that have been created using malloc. It works by creating its own fake version of malloc. When your program wants to allocate some heap memory, Valgrind will intercept your calls to malloc and free and run its own versions of those functions. So it replaces your stock malloc and free with its own version that adds like tracking and other like bookkeeping things to help you out in terms of detecting memory leaks. If it didn't do that, then it has no idea what's going on. So every time it like maybe I'm guessing underneath the hood when you call malloc using with Valgrind, um, it will basically how should I say this? It'll basically say, okay, you're calling malloc. I'm gonna record that you allocated this much memory into with this pointer here, and then it'll kind of when you call free, then it'll go look back at that record and go, okay, you freed it. Okay, I'm gonna cross this out, and then by at the end of like your program execution, most likely it's probably gonna refer to this like table and say, oh hey, you didn't actually handle freeing up this entry or this entry of memory. So I think that's how maybe it works like that underneath the hood. Of course, it's gonna be more complicated, but it's just my guess, which is why I would need to like intercept these calls. The Valgrind version of malloc will take note of which piece of code is calling it and which piece of memory allocated. So yeah, just exactly what I just said. When your program ends, Valgrind will report back on any idea that was left on the heap and tell you where in the code the data was created. So yeah, first we need to prepare our code to add the debug info. You don't need to do anything to your code before you run it through Valgrind. You don't even need to recompile it. Hey, I remember this. We just read this a couple days ago. Okay, so yeah, I'm just gonna keep reading it again. But it turns out you do need to recompile it. But whatever. But to really get the most out of Valgrind, you need to make sure your executable contains debug information. Debug information is extra data that gets packed into your executable when it's compiled. Things like the line number in the source file that a particular piece of code was compiled from. If the debug info is present, Valgrind will be able to give you a lot more details about the source of your memory leak. To just add debug info into your executable, you need to recompile the source with the G switch. Okay, so let's do that. Let's do that. Let's do that. Okay, so I'm already here. I think I had already compiled it once. So gcc main.c, and I'm going to do -g, and that should just recompile everything. Okay, so I noticed usually it's like 16 kilobytes, but now it's like 19. So that's a good sign. It's probably added a bunch of debug information. That's how I can tell. Because if I didn't compile with -g, oops, then we would have a much smaller file in our executable. But because we compiled with -g, it probably added a lot of that debug information in debug metadata, whatever you call it. Okay, so to see how Valgrind works, let's fire it up on a Linux box and use it to interrogate the spy's program a couple of times. Okay, to the first time, use the program to identify one of the built-in suspects, Vinny the Spoon. You'll start Valgrind on the command line with -- leak-check equals full option and pass it the program you want to run. So basically, Valgrind -- leak check full and then the program. So in this case, it'll be /a.out for us. So let's do that. Valgrind -- leak check equals full. Then the program we want to run -- oh, we don't have Valgrind, but we can just install it. So sudo apt install Valgrind. That will install Valgrind. And then try again. Cool. So great. So notice how it's going to run the program like normal, except that it looks like a different I guess shell now. It's just actually running inside this environment that Valgrind has created for us. So if I say yes, like the example here, Vinny the spoon, yes. Suspect identified. I'm gonna say no, don't run again. And it says all heap blocks were freed, no leaks are possible. So we didn't leak memory in this instance here, but we can go further. So to see how Valgrind works, let's fire up a Linux box and use it to interrogate the spy's program. Okay, so we did all that with the leak check full, and then we're gonna use Valgrind repeatedly. So this is like the debug process. We're gonna keep doing this pattern in terms of trying to reproduce a memory leak. So we use Valgrind repeatedly to gather more evidence. When the spy's program exited, there was nothing left on the heap. But what if you run it a second time and teach the program about a new suspect called Hayden Fantouche? So let's do that again. So no need to recompile with -g because we've already done that. We just need to run the program again. So we're here now, and we say the suspect doesn't have a mustache. Is it Loretta Barnsworth? No. Who's the suspect then in this case? Oh, I suspect Hayden Fantouche. Okay, give me a question that is true for Hayden Fantouche, but not for Loretta Barnsworth. Okay, I say has a facial scar. Okay, run again? No, I don't want to run again. Okay, so now we get something different. We have a suspected memory leak. So in use, we have 19 bytes left on the heap, and then we had 13 allocations, 12 frees. Okay, so let's say so here, same thing. Okay, but this one's 11 allocs, 10 frees, sure. Basically, you had 11 allocations, there were 10 frees, so one of them didn't get free. So for us, it's 13 allocations, 12 frees, one of them didn't get free. Okay, so 19 bytes and 1 blocks are definitely lost in lost record 1 of 1. So here's the stack trace. And if you look at the stack trace, we looked at it came from a stirred up malloc. So that's pretty cool. It came from the create function. So it goes up, right? From main to create to stirred up. So we know that it's leaking from when we actually created this new question node. Okay, and it has to do with the stirred up. Okay, so this time Valgrind found a memory leak. It looks like there were 19 bytes of information left on the heap at the end of the program. Valgrind is telling you the following things. 19 bytes of memory were allocated but not free. It looks like we allocated new pieces of memory 11 times but only freed 10 of them. Do these lines give us any clues? Of course it does. It's so cool that it does, right? Why 19 bytes? Is that a clue? Yes, that's quite a few pieces of information. Let's take these facts and analyze them. Okay, so time to look at the evidence. Okay, let's go back to our IDE. Okay, so we know that it came from create, from a malloc here, stirred up here. Internally stirred up probably does a malloc too, which is why. So, yeah, let's see if I can get into here. Nope, can't. Okay. Okay, so location. You ran the code 2 times. The first time there was no problem. The memory leak only happened when you entered a new suspect's name. Why is that significant? Because that means the leak can't be in the code that ran the first time. Looking back at the source code, that means the problem lies in this section of code. So the part where the second part where we had to execute, I guess, this part, this else part, where we had created the suspect, is most likely the part where the leak came from. Because the first time when we identified the suspect, we didn't get a leak. But now when we go to this path, we ended up getting a leak. Okay. All right, sure. When you ran the code through Valgrind and added a single suspect, the program allocated memory 11 times, but they only released memory 10 times. What does that tell you? Valgrind told you that there were 19 bytes of data left on the heap when the program ended. If you look at the source code, what piece of data is likely going to take up 19 bytes of space? Well, it's probably a string in this case. This fgetS here is 20, right? So with that null terminating character, maybe that gives it 19. So let's see. Finally, what does this output from Valgrind tell you? So yeah, again, from main at line whatever, in this case for us, it is main 45 to 20 to 42. So main at 45, where's 45? Okay, main at 45. Okay. Then create 20. Okay, so it's stirred up. It's stirred up. Okay. So how many pieces of data were left on the heap? There's one piece of data. What was the last piece of data on left on the heap? The string Loretta's Barnsworth. It's 18 characters with the string terminator. Okay, so yeah, it was a string, but except not this string. It was literally the Loretta Barnsworth. Okay, which line or lines of code causes? The create functions themselves don't cause a leak because they didn't in the first pass. So it must be this stirred up line. Yeah, stirred up. Because stirred up, it's screaming at stirred up here too. Okay, so this line here, current question stirred up question. Okay, so let's see here. Right here. Or was it? Oh, right here. Okay. Huh, okay. So, oh yeah, that makes sense because we didn't leak when we went here, but we leaked here. And I guess when we created the suspect, we had a yes node that's created allocated pointers, but then what ends up happening is, okay, so these nodes get created and assigned to these pointers, and then the question gets created too. But when we release, I guess what ends up happening now is we free things, but also we don't end up freeing the question associated with it. Interesting. So current has to be linked with at least something here. Current start node. Okay, if we say, well, it's not any of these, then the current question gets reinitialized pretty much, if that's the case. Okay. Oh no, it gets create start node. Yeah, Loretta Barnsworth. We create that. We create the node. Does the suspect have a mustache? And then we start current here. Okay. And then we say, well, yes, no, current question. I think we said no. The suspect has a mustache? No. We said no. So that returns false. Else if current no. Okay, Loretta Barnsworth. Okay, current equals current, no. Okay, so that moves a pointer there. And in the next iteration, I think what ends up happening now is that that Loretta Barnsworth has a null. So this doesn't apply. This doesn't apply. So now we ask and we create. Oh, I see, I see, I see. So then because of that now, we have this null here that gets created with the string. And then does that ever get linked? Yes, because that's here. Okay. And that was the old one. That was Loretta Barnsworth before, but we're overwriting it now. So what ends up happening is that before it was Loretta Barnsworth, and then now we're overwriting the question with a new question. And what happens to the Loretta Barnsworth string? It's left in the heap now as we change the pointer, the question to like the new thing that we're inputting. Okay, this makes sense. So how do you plug the leak? Uh, if current question is already, oh wait, yeah, if current question is already pointing to something in the heap, free that before allocating a new question. Oh, okay. So free current question before we actually create a new question on top of that, so we don't lose it. Okay, so let's do that. Okay, so now that we fixed the code, we have to recompile it and then run Valgrind again. So let's do that. So gcc-g, because that gives us debugging information, main.c. And then we can run Valgrind with leak checks equal full with our compiled program. And then we can run it again. Does suspect have a mustache? No. Loretta Barnsworth? No. Who's the suspect? Hayden Fantucci. And then give me a question that's true for Hayden, but not for Loretta. I say has a facial scar. And then I say run again. Nope. And then all blocks are free. So we had 13 allocs, 13 frees in this case. So that's good. Okay, so the leak is fixed. You ran exactly the same test data through the program. And this time the program cleared everything away from the heap. How did you do? Did you crack the case? Don't worry you didn't manage to find and fix the leak this time. I don't think we did. It was pretty tricky. Memory leaks are some of the hardest bugs to find in C programs. The truth is that many of the C programs available probably have some memory bugs buried deep inside them, but that's why tools like Valgrind are important. It helps you spot when leaks happen, identify the location where they happen, and it allows us to check to make sure the leak is fixed. Okay, there are no dumb questions. Valgrind said the leak memory was created on line 46, but the leak was fixed on a completely different line. How come? The Loretta Barnsworth data was put onto the heap on line 46, but the leak happened when the variable pointing to the current question was reassigned without freeing it. So you have to remember, if you had mallocked something, okay, if you mallocked something to a pointer, meaning you allocated memory and then got that pointer to that memory and assigned it somewhere. If you repoint that pointer to somewhere else, that part of the heap that you had just allocated before stays there. So we have to remember to free that. Okay? Yeah, that makes sense. Okay. Uh yeah, leaks don't happen when data is created. They happen when programs loses all reference to the data. Can I get Valgrind on my Mac, Windows, or FreeBSD system? Check Valgrind for details on latest release. And this is why I chose to do all this on Linux, because uh, I just don't want like complicated setup. I just want something super easy and just works. And fortunately, when it comes to C programming and things like that, Linux is just so much easier. So, um, how does Valgrind intercept calls to malloc and free? The malloc and free functions are contained in the C standard library, but Valgrind contains a library with its own versions of malloc and free. When you run a program with Valgrind, your program will be using Valgrind's functions rather than the ones in the C standard library. So why doesn't the compiler always include debug information when it compiles code? Because debug information will make your executable larger, and it may also make your program slightly slower. Where did the name Valgrind come from? Valgrind is the name of the entrance to Valhalla. Valgrind, the program, gives you access to the computer's heap. I guess that's Valhalla? Okay. Bullet points. Valgrind checks for memory leaks. Valgrind works by intercepting the calls of malloc on free. When a program stops running, Valgrind prints details of what's left on the heap. If you compile your code with debug information, Valgrind can give you more information. If you run your program several times, you can narrow the search for the leak. Valgrind can tell you which lines of code in your source which lines of code in your source put the data on the heap. Valgrind can be used to check that you fixed the leak. Cool. So yeah, we've learned we finished another chapter. Okay, cool. Moving on. So now we've learned how to use dynamic memory, so we can actually create data structures that aren't fixed in size, so we can just dynamically allocate things and add more elements to like lists that can grow indefinitely. We've also learned how to free that memory. Now it's time to understand that we can actually take functions and pass references of those functions around so that we can actually use those references to dig into that function and call it. And if you've programmed JavaScript before, it's kind of like passing a callback function to every function call. That callback function is just basically that function reference that then that other function can use to just call it. It's similar here in C. So yeah. So turn your functions up to 11. My go on date is awesome now that I've discovered variadic functions. Basic functions are great, but sometimes you need more. So far, you focused on the basics, but what if you need even more power and flexibility to achieve what you want? In this chapter, you'll see how to up your code's IQ by passing functions as parameters. So your arguments to a function can be those arguments can be functions themselves. So your function arguments could be functions too. That's so cool. You'll find out how to get things sorted with comparator functions. And finally, you'll discover how to make your code super stretchy with variadic functions. Okay, so functions that take a number of arguments, I guess, like any number of arguments. Looking for Mr. Right. You've used a lot of C functions in the book so far, but the truth is that there are still some ways to make your C functions a lot more powerful. If you know how to use them correctly, C functions can make your code do more things, but without writing a lot more code. To see how this works, let's look at an example. Imagine you have an array of strings that you want to filter down, displaying some strings and not displaying others. So we have basically a 2D array of strings. And I guess the number adds is 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the number, so it's like an array of strings with 7 strings in them. Okay. Okay, I want someone into sports, but definitely not into Bieber. Sure. This is when Justin Bieber was still super popular, I guess. Let's write some code that uses string functions to filter this array down. Okay, code magnets. Complete the find function so it can track down all the sports fans in the list who don't also share a passion for Bieber. Ooh, let's play around with this. So let's take a screenshot, and I think we have all these to play with. Then we can work on this together. How do I resize this? Oh, this one? Yeah. Okay, should be decently big. All right. Okay. Let's see if my pen works. Nope, I have to turn on my tablet. Okay. Hello, pair. Come on. It's pairing. I think it's pairing. Come on, Bluetooth. Connect. Great. Okay. So let's start. Okay. So it's just a filter function thing. So puts, let's see. We're asking where puts is going to be something that will print out a string. So search results. Okay, so that's this is not I thought it was dotted. Okay, so this is just a regular string. Okay. For I equals 0, and I'm guessing based off of whatever that person wants to find, we want to go through the entire list of ads. So this is going to be like some sort of less than here, which is this one. And then we're going to say num ads, which is a number. So 7 maybe. So that's the one. So we'll say num ads if let's see, stircomp, maybe stircomp or stir. I think stir is the one that looks for substring, right? So let's see, man stir. Stir finds the first occurrence of the substring. Yes. So stir maybe stir. So if stir okay, if stir takes in what? Takes in the haystack, which is like the big string itself, and then the needle, which is like the thing they want to search for. They want someone into sports. Was it sports that she wanted someone in non-sports? I want someone in sports, but definitely not into Bieber. Okay, so stir of adds I, which is the current element. So adds I stir. Sports, meaning that's contained in that string. And what is this? I guess and not into Bieber. Not falsy. We want falsy. Stir. Adds I. So we don't want it. We don't want any Bieber in this. In these strings. Okay. Then we want to print basically the ads. So that's good. I think this is our solution. So we'll iterate through every single ad defined by num ads, which is the number of total ads. We're going to want to compare to see if sports is contained with inside that current ad, right? In index I. using stir, and we want to make sure that that specific add, that same add with adds I, does not have Bieber. So I think, yeah. So yeah, lessen them adds, stir. Guess we stir adds sports, and then and not stir adds Bieber. Cool. Pretty good. So now if you take the function and the data and wrap everything up in a program called find.c, you can compile it and run it like this. Okay, gcc find.c -o find and execute find. So given the ads, you want to search for sports Bieber, so William and Josh. They both like sports, but they don't mention that they like Bieber. And sure enough, the find function loops through the array and finds the matching strings. Now that you have the basic code, it would be easy to create clones of the function that could perform different kinds of searches. Hey, wait, clone the function? That's dumb. Each version would vary only by like one line. Exactly right. If you clone the function, you'll have a lot of duplicated code. C programs often have to perform tasks that are almost identical except for some small detail. At the moment, the find function runs through each element of the array and applies a simple test to each string to look for matches. But if the test that it makes is hardwired like this right here, where we had to search for sports and Bieber explicitly, that means we can't really search for anything else like arts, theater, or dining. So what if we need something very different? Do we have to create separate functions for these, like find, like sports, but not like Bieber? Find underscore arts underscore theater. Find underscore arts underscore not underscore dining. Like we had to have all these different combinations of functions. That's not going to scale. So we need a little bit more something sophisticated, something that we can just plug in right here in this check here to see if we need to print this add. Something that can just replace this area here. We basically can pass code to a function. So what you need is some way of passing code for the test to the find function. Okay. All right, so I'm gonna finish this and then I have to run. So if you had some way of wrapping up a piece of code and handing the code to the function, it would be like passing the find function to a testing machine that it could apply to each piece of data. Okay, so basically each one of these is like an add. And this testing machine is like the code that you run to filter out. So this whole thing here, this whole mechanism here is your function, your main function, this find function. But this testing machine, this was the one that you can swap in and out, which is this code here. It's going to be just another function call, really. And what you want is to change this argument here to be a function. So then say, find, and then parentheses, my test func. And then here it'll be like, if my test func is true, calling my test func, then we'll print the add. So that's basically what this testing machine is. So this means the bulk of the find function would stay exactly the same. It would still contain the code to check each element in an array and display the same kind of output. But the test it applies against each element in an array would be done by the code that you pass to it. Cool. All right, I'm gonna stop here. So we'll continue again later. Thanks.